So hello everyone, welcome back. Today we are going to complete the one shot for atomic structure. So let's begin it. Give heading atomic structure. Atomic structure. Okay. Now the first thing which we learn in this chapter is the few formulations, and then we will apply the few formulation meanwhile while doing the sums. Okay, so let's start with the first category of the formula which comes in this chapter. It's from electromagnetic radiation. Okay, so let's give the heading electromagnetic radiation. Right. Okay, so under electromagnetic radiation we come across a formula which says C equal to nu lambda. Okay, here C is speed of light. Okay, nu is frequency, and lambda is your wavelength. Okay, this is our formula number 1. Okay, now under this category a second type of formula comes from here which says that lambda bar equal to 1 by lambda. Okay, lambda bar is called wave number. Okay, so by substituting this you can write here equal to, now see, this is C equal to nu lambda. I am just doing for your understanding. Okay, C equal to nu lambda. Okay, we substitute lambda, it becomes C by nu. Okay, now we put lambda over here. Okay, so it will become the reciprocal, so it will become nu by C. Okay, but the main formula is this one, C equal to nu lambda. Okay, here you have to keep in mind that speed of light is equal to 3 into 10 to the power 8 meter per second. Right. So this was the formula of the electromagnetic radiation, which is C equal to nu lambda. Now we come to the second portion. This is a theoretical part which you have to remember, that is the electromagnetic spectrum. Okay, so let's make a partition over here. Give a heading electromagnetic spectrum. Okay, now this is a spectrum of band of the order which I will give you will be of increasing wavelength and decreasing frequency. See, from here, from this relation, okay, when you see frequency is increasing, that means lambda is decreasing, right? This is an inverse relationship function, right? So I am going to give you a series. It will be moving from this side to this side, from this side from my right to from my left to my left. Okay, so let's write the series first. First will be cosmic rays. Cosmic rays. Okay, the next one will be gamma ray. Next, X-ray. After that, UV. Okay, next is visible ray. Visible means the waveguide which we see, the colors which are visible by the normal human eye is called the visible ray. Okay, this range is not visible. Okay, after visible ray comes infrared, IR. Okay, and after that we get a ray which is called microwave, and at last we get radio wave. I am putting the comma here, radio wave. Okay, now from this side to that side, okay, I am giving an arrow from this side to that side, the wavelength is increases and frequency is decreasing as they go from this side to that side. Now this series is very difficult to remember. I give you a trick which you can follow. Okay, so I am writing out a trick or a mnemonic over here. Okay, you can say classical Gari XUV in my range. Okay, so I am writing here classical Gari XUV in my range. Okay, so this is the trick for remembering the electromagnetic spectrum. It is from cosmic rays to radio waves. As we move, the wavelength increases, and as a result the frequency will decrease. So copy up to this much. After this we will do some more formulations, and then after that we will solve some numericals. So copy it. Done. So let me just okay, now we next come to a topic which is called the Planck's quantum theory, which was given by Max Planck. So let's see what it is, what are the formulas in it. Okay, let's write over here, give heading Planck's quantum theory. Okay, the first formula in the Planck's quantum theory, which was given by Max Planck, it was E equal to h c by lambda. Okay, what is h? H equal to Planck's constant. Okay, what is c? C is as usual the speed of light. Okay, and lambda is your wavelength. Now see here, E equal to hc by lambda. Okay, now this c by lambda, we know c equal to nu lambda, right? Okay, that means c by lambda equal to nu, right? So we can write here equal to h nu. See, c by lambda is nu, so c by lambda is replaced by nu. Okay, so E equal to hc by lambda equal to your h nu. Okay, now this is for right here for one quanta. Okay, what is quanta? Quanta is packets of light, or you can say energy. Okay, so this is for one quanta. For getting space, I am rubbing out this you have to remember. Okay, h is Planck's constant, c is speed of light, and lambda is wavelength. Okay, so let's erase this. Okay, this one also. So E equal to hc by lambda equal to h nu. Next one Now this is for one quanta. Now when quanta is n, okay, then the formula becomes E equal to nhc by lambda, okay, or you can say nh nu, okay, for n quanta, right? Okay, now see here this h, okay, let's do. Now see here, if we copy the same thing over here, it is coming E equal to n hc by lambda, okay. H is the Planck's constant and 3 is the speed of light. Now since both of these are constant, so after calculation the product of these two things, means the Planck's constant and the speed of light, the formula becomes equal to E equal to n, okay. Now I will write the product of these two values h and c. It is coming equal to your 12400 by lambda, okay. So for the sake of your convenience, if you remember the value of h or you remember the value of c, then you can easily put and find out the or solve the problem. But for your reference purpose, it is better to remember this 12400 in place of in case of this two, because it will simplify your calculations, okay. And here you have to remember that lambda should be in angstroms. We know angstrom is a unit, okay. So this is E equal to 12400 into n by lambda. N is the number of quanta, okay. Now in all the cases the energy is measured in electron volt. So let's write here electron volt, okay. Now these things it can be in electron volt also, it can be in joules also, but this formula is only applicable for electron volts, okay. I give you a relation where you can get the relation between joule and electron volt, okay. So remember, I am writing out over here, putting crosses, okay. Remember, sorry, remember 1 electron volt equal to 1.6 into 10 to the power minus 19 joules. So this is a relation which you can bring to use while solving the numericals, okay. So copy up to this much. After this we will do some numericals. Done. So let's erase this and solve some numericals. Okay. So what was my formula? My formula was E equal to n into 12400 by lambda in angstrom, and this was in electron volt. So this is my formula which is going to come to use just now. So I am keeping this for sake of convenience. Okay, right. Now the question says find the energy. So you need to find the energy of photon whose wavelength is wavelength is 320 nanometer. Okay, so 320 nanometer. Now keep in mind this is given in nanometer. You need to convert it to angstrom while solving. Okay, so this is the question: find the energy of photon whose wavelength is 320 nanometer. Okay, so let's begin. So what is given? Lambda equal to 320 nanometer, right? So 320 nanometer, I can convert it to, okay, let's take this not 320, let's take it 310. Okay, calculation will be easier. Okay, so 310 nanometer, let's convert it to angstrom. Okay, so it will be 3100 angstrom, right? Clear up to this much? This was lambda was given in nanometer, and so I convert it to angstrom. It comes 3100 angstrom. Now I will directly put this formula for my better calculation. Okay, if you want, you can put the value of constant of light and also the Planck's constant, and you can evaluate. The answer will come more or less same. Okay, so let's find out. So since the number of photon is not told here, so we will take unity, that is 1. Okay, so let's take n equal to 1. So E equal to 1 into 12400 by your 3100, right? So how much this is coming? So with this I cancel out. Now see, this one is 31 4s are 124. So the answer is coming 4 electron volt, right? But if the question was said, okay, if the question was like this, where they told you to find in joules, okay, then I have to do nothing, E joules. Okay, so what I have to do is I multiply simply 4 into 1.6 into 10 to the power minus 19 joules. So the answer will come around 6.4 into 10 to the power 19, 10 to the power minus 19 joules. So this is your answer. Okay, so this was a very simple and basic question in this Planck's theory. After this, let us now discuss the Bohr theory about the Bohr radius and the velocity of an electron. So copy it up to this much, then I will rub the board and then we will continue further. So copy it. Done. So let's continue. Just a minute, let me drink some water. Okay, let's move on. Give heading Bohr's theory. Okay, so Bohr's theory was given by a famous and very well established mathematician who was called Niels Bohr. He was an excellent mathematician and his name was Niels Bohr. Just a minute. Okay. So Bohr's theory. Bohr's theory. Now before studying Bohr's theory, you have to remember that Bohr gave this theory only for isoelectronic species or hydrogen-like species, and you know hydrogen is isoelectronic, right? And isoelectronic species not only means hydrogen, it can be Ag plus, it can be your Li2 plus, it can be your Bi3 plus, and like this. That means there has to be one electron. You cannot deal with multiple electronic system. Okay, so I write here, where I write, for 1 E minus systems. Okay, example, hydrogen, He plus, helium, Li2 plus, Be3 plus, and so on. Right? Now Bohr gave the formula for the orbital angular momentum. What is the orbital? Orbital is the region or space where the probability of finding an electron is maximum. Okay, so Bohr gave the orbital angular momentum. So number 1, formula for orbital angular momentum. Okay, so orbital angular momentum, Bohr gave the formula. We know it's mvr equal to nh by 2 pi. So this was the formula for orbital angular momentum, which was given by Bohr. Okay, next we come to the radius of orbit, that is the radius of the orbit in which the single electron or isoelectronic species in an isoelectronic species is revolving and rotating. We need to know the radius of the atoms. Okay, so and this radius of the isoelectronic species, you have to remember, it is also called the Bohr radius. So in the question, if they ask you find the Bohr radius, okay, so you should not confuse yourself. Bohr radius is nothing but just the radius of the isoelectronic species. Okay, so let's write the formula. Radius of Bohr. Okay, now radius of Bohr, if we take it as r, so it is equal to r0 into n square by z. Okay, now this r0 has a value which is equal to 0.53 into n square by z, but this will come in angstrom, right? So r equal to 0.53 into n square by z angstrom, right? Clear up to this much? And this r0, this is not radius of atom, it will be radius of atom, I'm sorry. Okay, and this r0 equal to Bohr radius equal to 0.53 angstrom. Okay, clear? So this was the radius of the atom or the radius of the orbit in which the electron is rotating. So let's change this to radius of orbit to be more precise. Now the third thing which comes in this category is the velocity which which the electron is rotating in the orbit. So give the heading velocity. So the formula for velocity which was given by Bohr by performing various derivations. I told you that he was a great mathematician. Okay, so after giving various derivations, he came to the formula of velocity, which is v equal to 2.18 into n square by z was for this radius of the orbit, and in this case it will become z by n. Okay, z is the atomic number. So this is in meter per second. So it's 2.18 into z by n meter per second. Okay. Now the total energy of the electron in the orbit. Okay, total energy. So Bohr gave this formula by deriving, it is equal to minus 13.6 into 10 to the power 6 into z square by n square electron volt per atom. Please keep in mind about the units. Okay. Number 5. Now about the kinetic energy. Now see, kinetic energy is nothing but the same thing but the negative of this. That means this will be 13.6, let's write it this way, minus TE. Okay, total energy I am taking as TE. Okay, so kinetic energy is equal to minus TE equal to 13.6 into 10 to the power 6 into z square by n square electron volt per atom. Right. Number 6, potential energy or PE equal to 2 into KE, which is equal to 13.6 into 10 to the power 6 into z square by n square into 2 electron volt per atom. Okay, clear up to this much? So let's make it a bit more clear so that it is easier for you to copy and don't get confused. Let's make some markings. All right, I have my pens. So what is the first thing we learned? The first thing is the orbital angular momentum, which is mvr equal to nh by 2 pi. So let's box it out. Okay, next thing we learned is the radius of orbit, this one. Okay, moving on, the next one was the velocity. What is the velocity? Velocity is coming 2.18 into z and by n meter per second. Okay, it's becoming untidy. Surely, let's not do this. Let's keep it clean. Okay, so this is the velocity, this is the orbital angular momentum. Next we came to the formula for total energy, which is 13.6 into 10 to the power 6 z square by n square. This is kinetic energy is negative of total energy, which comes 13.6 10 to the power 6 z square by n square, and potential energy comes 2 into twice of kinetic energy, which is 13.6 into 2 into 10 to the power 6 into z square by n square electron volt per atom. Okay, so copy up to this much. Next I will move to the formula for ionization enthalpy and the binding energy and excitation energy. Okay, so copy it up to this much, then I'll go. Copy it. Now for this you have to remember that it's only for isoelectronic species or for one electron system. Okay, so let's clear it out. So let's clear it out. All right. So the next formula which we will learn is the ionization energy. Okay, so ionization energy is what? The minimum amount of energy that is required to isolate an electron from the outermost shell of an element. So isoelectronic species for hydrogen means to take out the electron from the outermost shell of hydrogen, the amount of energy which we are going to expend from the outside is called the ionization energy. So that has a formula. Let's write it. Ionization energy, which this will be number 8, I guess. Ionization I'm sorry, enthalpy, right? So what is the formula for ionization enthalpy? It is equal to 13.6 into Z square, okay, and the unit is electron volt per atom, okay. After ionization energy, we come to the formula of binding energy, or let's do the formula of ionization. Let's do the formula for excitation energy before it, okay. So formula for excitation energy. So the formula for excitation energy is 13.6 into Z square into 1 minus 1 by n square, and this is also in electron volt per atom, right? And number 10 and the last one is your binding energy. Okay, which is equal to 13.6 into Z square by n square. Clear up to this much, right? So this thing you can see is equal to, compare this thing and this thing. So if ionization energy, I take it as IE, so I can say here it is equal to IE by 2, right? So this was the formula for binding energy, that means the energy with which the electrons are bound around the nucleus. So copy up to this much. After this we will come to the formula for the time period, and thereby we will also discuss how the frequency is changing with, or how frequency is depending upon the time period. So copy up to this much, we will learn about the time period. Copied. So I rub it, right? So let's clear it out. So it will be number 11. So number 11. So time period. So time period is directly proportional to n cube by z square. Now what is time period actually? Time period, we know, if this is the nucleus, okay, and this is the electron rotating in its orbit, okay. Now if this is the electron over here, okay, the electron, I take a point, okay, I wait for the electron to come again. So the electron will recover the entire circle and again come back to this position, right? So the time taken by the electron to complete one complete rotation around the nucleus of the atom is called the time period. So time period has the formula of n cube by z square given by Bohr, okay. Now what is frequency? Now you have to remember that frequency is equal to 1 by time period equal to z square by n cube. Now what is frequency? Frequency is the distance or the time period in 1 second, that means the in 1 second how much the electron is covering, okay. So which is inverse of time period, so it is coming z square by n cube. So copy it up to this much. Now I will do some numericals from the Bohr's atomic theory. So copy it, I will bring the numericals. Done? Okay, so let's begin. Write the question. Let's write the question with a different color. So let's begin. Okay. Question. Find the radius, velocity, and what else was there? Total energy, kinetic energy, potential energy, and anything else. Let's keep up to this much. For He2 plus in, let's take first excited state. First excited state. Now for doing this, you have to keep a thing in mind that make a note while doing this. Okay, note. Third excited state means n equal to 4. Fifth excited state means n equal to 6. Okay. So like this, if it is given third excited state, then you have to take n equal to 4, that means 1 increased, and if 5, then you have to take 6. So here it is said for first excited state, that means here n equal to 2. So let's solve it here. So let's write with my black ink again. Here n equal to, since this is first, so this will be 2, and helium is atomic number 2, so it will be Z equal to 2. Okay, now I have to find the Bohr's radius. So number 1, this is R. We know R equal to 0.53 into n square by Z, which is 2 square by 2, equal to 0.53 into 4 by 2. So 2 and 4 get cancelled up, so it comes 0. I'm sorry, this will be 6, 0, 1.06. So this will be in angstrom. Okay, done. So this was about finding the radius of the orbit or the shell. So next question is asking you to find out the velocity which which the electron is moving around the orbit. So the formula for velocity, if you remember it, it was 2.18 into Z by n, and the what is the unit? The unit is meter per second. So let's find out. So velocity is 2.18 into Z by n, it is coming 2 by 2 equal to 2.18 meter per second. Clear? All right. Okay. Next we will find out the total energy. Okay. So total energy number 3. So T was equal to minus 13.6 into 10 to the power 6 into Z square upon n square. So it will be 2 square upon 2 square. So I am writing it 4 upon 4. So it comes equal to 1. So total energy equal to minus 13.6. This was in electron volt. 13.6 into 10 to the power 6 electron volt. Okay. Electron volt per atom, I'm sorry. Since single atom is given, so it needless to mention, but better to in the safe side mention the unit completely. Okay, next part they are asking about the kinetic energy. Now we know kinetic energy equal to minus of total energy. So this was already in minus, so if I put another minus, so it becomes a positive, right? So kinetic energy is equal to 13.6 into 10 to the power 6 electron volt per atom. After that they are asking for the potential energy. So potential energy is kinetic energy into twice, equal to 2 into Ke, equal to 2 into 13.6 into 10 to the power 6. Answer comes 2, 3 to the 6 and 1 7, 2 1 the 2, 2.72 into 10 to the power 6 electron volt per atom. I hope this portion is visible. Let me check. Yes, fine, this is visible. So next let's make this one a bit more prominent. So it is coming 2 6 are 12, 2 3 to the 6 and 1 7 and 2 1s are 2 into 10 to the power 6 electron volt per atom. Okay, so this was a numerical from the Bohr's atomic theory. So copy it. After this we will move to the hydrogen spectrum for the where we will learn about the Rydberg's formula, and that's so copy it. I am coming. Okay, so let's start. Next we come to the hydrogen spectrum. Okay, let's give the heading hydrogen spectrum. Hydrogen spectrum. Okay, now hydrogen spectrum has the formula. You need to find the, so the question comes this way, you need to find the wavelength of the values will be given when electron jumps from this subshell to that subshell. So you need to find out the frequency, or I am sorry, the wavelength of the energy emitted. I will give you the formula, and with that energy you have to say in which band. Okay, so band series will also I will show you in which band the energy, or the in which region the light will fall. Okay, so just a minute. Okay, so let's start hydrogen spectrum. So it is coming lambda bar equal to 1 by lambda equal to RH into, here you have to multiply z square into 1 by n1 square minus 1 by n2 square. Okay, what is RH? RH is called the Rydberg's constant. What is n1 and n2? n1 is the lower energy state and n2 is the higher one. Lower energy state and this one is higher energy state, right? So this is the formula, and RH has a value which is equal to 1.1 into 10 to the power minus, or not minus, it will be 10 to the power 7 meter inverse. So this is important. Okay, so copy it. Now I will give the hydrogen spectrum series So now I will give the hydrogen spectrum series, where you can easily put the values and get the lambda, and then you can easily predict in which band the electron jumps. Okay, so copy it. Copied. So let's clear it out. Now here you can determine the number of bands or the number of lines or spectra which is generated. So before that, let's know the series. Okay, so give the heading series. Now a line. Okay, now here will be value of n, and here there will be band. First series which comes for n equal to 1, let's make it 1, 2, 3, 4, 5 and 6, right. So the first thing which comes is the Lyman series. Next is Balmer series. Third is Paschen series. Okay, now after this it comes the bracket series. Okay, after bracket series is the fund series, but it is called P fund. P is silent. P fund. After that it is the Humphrey series, right. Now for Lyman series, it is the band which follows the Lyman series, it is the UV rays, which is the ultraviolet rays. Okay, the Balmer series follows the visible range, or you can say this is lambda. Okay, so you have to compare the value of lambda and determine. This one is IR, this one is IR, this one is also IR, and this is far IR. IR only, but more far. Okay, so copy it up to this much. Next we will do few sums. Let's copy it. Copied. Okay, so before doing further, let's write another formula here. Okay, let's write the formula: total number of spectral line, okay, which is represented by delta n. Total number of spectral line. Okay, so the formula is delta n into n plus 1, delta n plus 1 whole divided by 2. What is delta n? So I am writing here delta n equal to, this is n2 minus n1. Okay, so n2 minus n1. Okay, the next thing which comes is the total number of spectral line in a series. Okay, so it comes delta n minus n dash, where n dash is your series number. Series number means these things. Okay, so done. So copy it. After this we will do some numericals. Done. So let's move on to the numerical. Give the heading numericals. Okay. So give the heading calculate the lambda of photon emitted when electron jumps from n equal to 2 to n equal to 1. Okay, let's take a in H atom. Okay, so the question is like this: calculate the lambda of photon emitted when electron jumps from n equal to 2 to n equal to 1 in hydrogen atom. So we know lambda bar equal to 1 by lambda equal to, so what was the formula? It was RH into z square by 1 by n1 square minus 1 by n2 square. Okay, so what is coming? 1 by lambda equal to 1.1 into 10 to the power 7. What is z? Z equal to 1, since this is hydrogen. And C, here n1 will be 1 and n2 will be 2. So 1 by 1 minus 1 by 4. Okay, so what is coming? 1.1 into 10 to the power 7 into, so if you solve this, it comes 4 minus 1 by 4, which is equal to 3 by 4. So 3 by 4. Okay, so if you are not interested to put the value, and if you find the option that this thing is coming, means you can get the option like this also: RH into 3 by 4 means 1 by lambda equal to Rydberg constant into 3 by 4th. So what will be lambda? Lambda equal to 4 by 3 1 by RH. Clear? So this was the formula. Like this type of question come from the hydrogen spectrum. So this was the first part of the atomic structure series. Video is becoming long, it will be difficult to upload. So keeping it up to this much, in the next video we will discuss about the de Broglie wavelength, then we will complete with the quantum theory. So for this, up to this much. Hope you like the series. Coming in the next video. Thank you.